Okay, so on the next slide we have a certain visualization of what we were talking about. So the first option is a base substitution mutation. So we see that originally the triplet representing a certain amino acid, which we call a codon, is supposed to be ATG. And now what occurs is that the G is replaced by a C. So ATC does not represent necessarily, and this is just an example, all right, the same amino acid as ATG. So this is a mutation, right, that is regarded as a base substitution. It might not be a big deal. It might not even affect the amino acid that is produced, because some amino acids have more than one codon for them. The second option, for instance, is a frame shift. So we have two examples here for a frame shift. Sorry. The first codon in this case is ATG. The second one is CTA. The third one is GAG. Okay? And now we have a deletion of one of the nucleotides. So you can see that the A is taken out. Suddenly, the reading frame shift has moved one nucleotide ahead. So from instead of being ATG, suddenly the frame shift starts from TGC. Okay, so we have a shift. Most likely won't result in a good outcome from us. And the other frame shift option is an insertion of a nucleotide. So the original is TGC, and suddenly the A is inserted before the T, making the new frame shift start from ATG. So it's basically the opposite than what we just talked about in the deletion. But the frame shift is going to affect everything after the location of the influence, either the deletion or the insertion. Whatever happened before was using the right frame shift, right? But wherever that mutation happened, it's one of those two mutations happened, is going to affect the rest of the frame shift in example 2 and 3. In example 1, it affects only that specific codon, not the whole molecule or the whole sequence. Does that make sense? I hope it does. A frame shift that is that occurs because of an insertion can be repaired or reversed, and a frame shift that is that occurs because of a deletion can be reversed by an insertion. So they kind of cancel each other, right? If we had an insertion, we can produce a deletion. If we had a deletion, we can produce an insertion. Okay, so basically you'll see the signs of plus and minus. Plus means that an insertion or addition occurred, and meaning that the mutation is a mutation that adds something to a gene, and a mutation that has a minus means that it's deleterious. Okay? Okay, so we can also have multiple mutations or combinations. So that's what we'll call a double mutant combination, which may contribute to the dominancy of the phenotype if they are of the same sign, meaning plus plus or minus minus. So it can actually affect the alleles and its dominance and the chance of a certain phenotype being expressed, right? At the same time, it can be plus minus or minus plus, meaning that if two mutations occur at the same time, they can either be both adding something to the molecule, to the chain, or both deleting, or one and one. It's endless, right? So, and so on and so forth. If the plus, if two mutations occur, let's say one takes off the base of G, a G base, and at the same time occurs another mutation that adds a G, they just canceled each other. But they happen randomly. It wasn't planned. So two mutations occurred randomly. One took off a base that is a G. One happened to add a base that is a G, and we got no effect. So the sequence is conserved, right? So in this case, we will say that the cancellation of the first mutation by the second is a suppression, and the second mutation is the suppressor. Okay? And then we go on to triple mutant combinations. Once again, it can be plus, 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 minus, 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 and all kinds of combinations. And in certain ways, it might perhaps have no effect or good or bad effect. Okay. Okay, so we're talking about the triplets and the codon, and since we're using triplets, that naturally says that every sequence can have 3 different frame shifts. Okay, so I think that's logical and easy to understand. If there's triplets, triplets are made out of 3 nucleotides. Every nucleotide represents a possible frame shift start point. All right? And this has to be true only if there is no overlapping. Okay? All right. Let's proceed. Okay, so the next slide shows you the 3 different frame shifts, option 1, 2, and 3, to a sequence that theoretically has only ATG in it. So the first frame shift would be ATG, the second would be TGA, and the third would be JAT. Alright, so, and you would of course get completely different codons that would represent completely different amino acids in theory. Okay, so this is theoretical. So if we have genetic material that includes only triplets coding for amino acids, we call that an open reading frame, or for short, an ORF. So an ORF is a sequence of codons, okay, of triplets that actually code for amino acids. Since there are 3 reading frames possible, only one can be the right one for a specific protein, because we just said if you play with the sequences, you're using the wrong frame reading frame, right? So a specific protein needs the right ORF in order to produce the right protein. I'm going to say that again. A specific protein must be read with the right ORF, or the sequence, the triplets, the codons, have to be read by the right reading frame, the right open reading frame, in order to produce the right peptide. And we talked about this, the right protein, we talked about this more than once, and we'll continue to do it So we have a unique codon that is, its symbol is AUG. And this codon solves the problem. Why does it solve the problem? Because this is called the initiation codon. The initiation codon is the sign that we talked about that tells the apparatus, the deciphering apparatus, this is where the triplets represent codons for amino acids for the protein. Okay, so that apparatus is looking for the AUG, and when it sees it, and understand that this is where it starts reading the triplets, the codons that represents the right amino acids for the right protein, assuming there's no mutations. But what happens if there's a mutation in the starting codon and the initiation codon? I'll leave that up to you guys and ladies, of course, to understand what are the implications of that. So now you have a reference to 2 movies. I hope you see both. And you need to click on every picture in itself for every movie. Okay, so how do we know where to stop reading the codons at the 3' end? So we need a termination codon, right? Or a few termination codons saying, hey, this is where the peptide stops. Stop reading. Stop adding amino acids. Because if you don't stop, what are you going to get? The wrong protein. Okay? So the termination codon represents the end of the polypeptide to be produced. In some cases, we will find multi-termination codons interfere and prevent the reading into protein. So that can happen too. That means that stop codon is in the wrong place, one or more. And suddenly, instead of keep reading those codons, the apparatus has a order to stop. So that is a gene that we will call a blocked gene, because something happened to incorporate to have a stop codon, a termination codon in the wrong place before it should be. Okay? And now the gene is blocked. The frame shift, the open frame shift cannot read the sequence in the right way, so it's simply blocked. In addition, the apparatus might jump over, so to speak, that stop codon and start reading the frame shift again from the next option it has. And that's going to change the frame shift. Okay, so it's either completely blocked or it's going to change the frame shift. And you have the movie here. So you see after in the slide after the movie, you have those circles at points 2 and 4 that represent a block. Now the frame shift starts at ATG, and then suddenly between the A, the next A, and the next TG, a block occurs. So the frame shift cannot read the next A as connected to the T. So it's going to assume that the next point of reading is the T. So we lost the A. It's as if it was deleted. It's actually there, but it's not being read. But it's exactly the same effect regarding the frame shift as if that A was completely deleted. So the frame shift jumped from what we see in situation 1 to situation 3, and suddenly instead of being ATG, the frame shift, the reading frame shift is now TGA. And now we see that a block happens to occur between the T and the G. So it's as if the T is not being read. It's as if it was deleted, right? Exactly like what happened to the A. So suddenly we have another frame shift, and for the second time, and now suddenly the frame shift, the reading frame shift is GAT. So we started with ATG. We had one block that made it TGA. Another block made it GAT. I hope you understand that the outcome is not what we're going to want, right? I don't even think it's going to be functional. Okay, so you have the explanation here, which I just gave you in writing. So what we're saying is that when we look at the gene, when we look at mRNA, and we look at the protein, they all have to be collinear. They all have to have that information that is transcribed, into mRNA, that is translated into protein in the right order. Any mistake there, if they're not collinear, we're going to have a problem, probably. Okay. What happens if all three reading frame shifts are frames are blocked? That means that we have complete failure for the coding of the protein, right? Because none of the reading frames can be used. Okay, let's see. So we're saying that in order to create a polypeptide of n amino acids, n representing a certain amount of amino acids, okay, some kind of number, we need n protein coding codons, right? Thus 3 times that number of nucleotides. Once again, 3 nucleotides add up to 1 codon, adds up to 1 amino acid. That's what's written here. And the amount of amino acids in a polypeptide is 1/3 of the amount of nucleotides that it has to have in order to be made, right? A ratio of 1 to 3. So we can use maps to map what we call the recombination map and the physical map. So the physical map is actually the presentation of the sequence itself, and the recombination map is a map that represents the processes that have made recombination possible and representing what went on. Okay? When we look at a map, when we're mapping a gene, the distances between mutations do not necessarily affect the function or the map created. So what I'm trying to say is that when we take a map and we start pinpointing the mutations, the distance between one mutation and the other does not give us a clear understanding of how it's going to affect function. Alright? Okay, we'll stop here and we will continue in the next video.